So here, when we say arrays, so we have to, we will start with the arrays first, and maybe though you might have got some introduction from other lectures. So we'll start with a quick overview of arrays. Then what is meant by spacing? Then we'll go for this uniform spaced array and all. And then we'll come to know and what is the excitation, how so when I excite uniformly, what will happen? When I excite non-uniformly, what will happen? Maybe 1 or 2 slides will be there. Okay, so that's what is the agenda of the topic today. And at the end, we'll also see so application of these arrays in the current technologies, like for example 5G. All know now the trend is, the buzzword is like massive MIMO everywhere, right? So we'll quickly cover that topic as well. Okay, so that is the agenda today. So with this, yeah, the outline is like we'll just sort of preliminaries. We'll spend some time on that, and then we'll start with the n element array and the broadside and Endfire arrays. There are a number of arrays are there, but I will only see very limited one. And a planar array, how it look like, and then we'll move on to phased arrays. So why we go for phased array, how the scanning is applied, obtained, and why it is required. Those things we will see there. And then I know just this till now the topic will cover upon this array. Then we'll go for the antenna evolution for example in telecommunication, especially in the mobile side as well as the base station side. And then we'll cover 1 or 2 slides in the massive MIMO. And then last slide will be a simulation perspective, so of the arrays. Okay, and this basically the above 5 topics on these all based on the Planar book. Basically I adopted their lecture notes as well, so because I did not find much time to prepare on my own, so I had something but I could not able to collate for the flow. So please bear with me, and we'll just quickly start with this. Before we move on arrays, so first we have to look at what are all parameters to be considered, because so the arrays, why we go for array, because in order to enhance the gain and also the radiation pattern, and you want to concentrate your power to a particular directions. Okay, that is what the most of the time the array is performing. And also it has certain flexibility over, for example, apart from array, the complement of this array, the similar function is done by, for example, reflectors and lenses and the horn antennas and all that. But what is the advantage we have here, that we need to look at it. And then so in order to move forward, so we have first to understand there are a few quantities are there for the antennas, and also we'll try to understand this rectangular to polar plot, so that we'll appreciate that later slides basically. So antenna has 2 parameters in general. Okay, in general. So but it has several more parameters, but I am concising my topic to 2 parameters. One is circuit parameters, the other one is space quantities basically. So why it is important? Because in a circuit quantities, when you design an array, the circuit quantity obtaining first circuit quantities will be a major challenge, because you have to design a feed network in order to match the feeds, and also with the certain amplitude and phase. So that's why the circuit quantities will come into picture. For example, antenna impedance. Antenna impedance, I mean to say the input impedance of the each element basically. The radiation resistance, that is for the radiation, and impedance matching we can quantify through VSW or S parameters or return loss whatsoever. Okay, then we have a space quantities. Okay, these quantities are deliverable kind of thing. So that is deliverable kind of products, because those circuit quantities will ensure that my whatever excitation I'm supplying, it fed to antenna. Okay, now it is antenna to radiate or suppress or whatever it may be. So so in order to find out how the antenna is behaving, yeah, my input has come, because for example, light is there, right? You have a wire, you have supply, you have given a supply. Now it has gone to till the socket. Okay, now it's up to the bulb to glow or not to glow. Okay, how it is glowing, that depends upon it. Similarly, in an antenna as well, we have space quantities. One is radiation patterns basically, then polarization. So from the radiation pattern is the one we will try to find out, and then the other are all derived parameters. For example, polarization, which polarization is in. By looking at the pattern, we can able to say, is it a circularly polarized or linearly polarized? Linear itself, we have a two kind of thing: horizontal, vertical, and what is the beam area, directivity, and power gain, effective aperture, and so on. Okay, so on the right, we can see that see rectangular to polar plot. This we need to understand because see the rectangular plot is like kind of an expanded version of the polar plot. Okay, so here what we infer from this plot. So thing is, see, when we look at this antenna radiation pattern, so antenna radiation pattern means what? So the power that is how it is distributed. So our antenna is radiating. So the radiated power, how it is distributed in the space in terms of theta, we can say as a function of theta. That is the radiation pattern basically. So that is what we are plotting here. Either you can plot in as an rectangular plot or a polar plot, one and the same. But only thing is that, see here, you can see clear cut. Okay, what is the side lobe level? With respect to this main lobe, what is the side lobe level? That we can see over here. Some convenience we have. But when you look at this one plot, a polar plot, what convenience we have is, for example, what is my back lobe? Okay, you can easily identify. So for example, if this is the antenna, this is my front lobe, let's say, okay, because it has some scanning kind of thing. So this is the front lobe and this is the back lobe, like that. So we can able to easily identify by looking at the figures. Yeah, this antenna is radiating in this particular direction. Okay, and it has this much side lobes, this many side lobes, and this many back lobes, and this many grating lobes, and other things. Okay, so that is the beauty of this polar plot basically. So why I'm concentrating this over here, because when you are going for an array, why we go for an array? So to suppress the side lobes and to enhance the power in to concentrate the power in particular direction in terms of gain, and to suppress the side lobes, to steer the beams. So for that only we go for an array. So in order to appreciate those results, so we should understand this polar plot. That was my idea here. Next is beam area, beam efficiency. So those are the, there are many more parameters are there. So I'm just quickly cover few things like beam area. So what is the area, beam area I'm covering? So beam area, so this will be a critical parameter in telecommunication perspective, because how much area I'm going to cover with my antenna. Okay, so within that coverage range, that is very important. Next is main beam area. What is the main beam area? Minor lobe area, which means see, this is the main beam area. So how much it is covering in a particular direction, how much area it is covering, and this how minor lobe covering this. So why it is important? Because some of the critical applications like military applications. So side what happens is instead of targeting this particular target, I may target this one. So that's why it is very critical there. And minor lobe area, how much is there, and main beam area, and main beam efficiency. So that is very important. So how much I'm having as general beam area and the main lobe beam area. So main lobe beam area should be as high as possible, so that that a beam efficiency will be high. Why? Because if you are having major lobe area is high, so what happens is you are unnecessarily transmitting power in this direction, in these areas. But rather my target is over here, but I am unnecessarily transmitting my power in these directions. That is why this minor lobe area, this beam efficiency is a critical parameter there in some of the applications. It depends upon the applications only. Okay, so that's why in defense and all, they always say that minus 30 dB side lobe level and 40 dB also. Some of the applications, most space application and all, they always target to have minus 30, minus 35, like that. Okay, because in order to enhance the beam efficiency. Next is this is the best visible difference you can see. For example, in 5G we will be covering this topic later, but I just as a beam is discussed over here, I will just show you how the power is getting wasted. See, this is the traditional power base station antenna radiation pattern, where you can see you are having only one device over here in the one sector, let's say, but you are radiating in entire direction, in this much direction basically. So what you are doing, you are wasting your power by transmitting in this particular direction. Rather, you are having your target over here, right? But in massive MIMO array, what they are introducing in from LTE onwards, they have started using massive MIMO. But some in terms of beamforming, there is a difference. In 5G, there is algorithm is different. Some of the applications is different. Use case is different, basically. And here you can see you are targeting, what you are doing with the help of an array. What I am doing, I am just concentrating power to a particular direction, where the U is there. So by doing this, what I'm achieving? So I'm improving the SNR, basically. And also my network is also very efficient, and also power requirement is becoming low. And indirectly what I'm doing, I'm doing good to the environment as well. Okay, that is the idea over here. Okay, and now let's move on to that topic of today, array. Okay, so array is not it's not any new topic there. So we could have seen in this kind of array in nature itself. Okay, you can see this flower. So there are array of kind of small stems and other things, and also you can honeybee, this one, and you can see the net, and also the insect. So some of the insect, you can see this kind of array pattern. Okay, so these are all the most of the inventions happen from the by looking at the nature itself. Okay, and the in terms of antenna itself, so you can see before antenna they introduce, say, not even antenna. So you can see that in LED lights also we have an array concept over here, because if you glow a single LED, it will not be visible for more than maybe 10 meter or so. But if you are using array of LEDs, then what happens? It will be visible for more than 100 meters. Okay, so that is the actual logic, basically. Okay, and that is the purpose of the array antenna as well. Similarly, speakers, if you're having one speaker, it will be audible for about 80 meters or 100 meters. If you're having array of speakers, you will be having, the audible, it will be audible. So that's why light and sound, all it will have, a kind of similar functionality. So that's Maxwell's invention was that only. So light waves is an electromagnetic wave. That was the major breakthrough invention he has made. Okay. And some of the array antennas we can see here. I think near Tirupati there is an array observatory. I think remotes and some observatory array is there. So like this, and you can see over here. And these are all the field deployable array, basically for the used for the extensively for the defense. And these are all some of the array, square kilometer array, like that they used to call it as, for the space applications, basically. Okay. Next you have this kind of array. Okay. Next, this kind of compact array as well we have. Okay, some of the small applications, basically. Okay, so here objective is to performance. Okay, the performance of the antenna, basically, and also efficiency. So by the parameter called increasing the gain. That's the only thing. The advantages here is, like, you can control the beam. Okay, control the power that is being transmitted in the particular direction of the beam, and also we can steer the beam as well. Okay, next is high gain and diversity gain. For example, some multipath propagation, this will come into picture in the massive MIMO, basically, where you have MIMO as well as an array. And so array signal passing, so why it is important? Because you can process the arrays in the received signal, and then you can do what wonder you want. Okay, that is the thing. For example, in the defense radar, right, radar tracking systems, so where how you are tracking the enemy's fly jet or our own jet. So because based on the signal that you are receiving from the array, then process the signal and then find out which direction it is, and nulling of jammers and no moving parts. Because in array, for example, if you want to steer the beam, right, you might have seen in the airport some antennas mechanically is rotated, right? Whereas if you are having this phased array kind of thing, but you don't have to move any parts, you can steer the beam electronically. Okay, but the thing is, it may not be feasible for the plus minus 90 or plus minus 180, but mechanically you can do around 360 as well. But in here the limitation is that. Next is high cost. Yeah, obviously, because if you are using reflector alone, you need to have a horn antenna and then a reflector. That's all. Okay, and the mounting structure, right? But whereas the array, then you have a lot of cost is involved, fabrication and all. I mean, in some cases it will be even cheaper as well. Some cases it will be costly as well. So the two options are there. Okay. When you want to make a apple to apple comparison, some applications you may have lower cost. Array will be a lower cost, cheaper solution, but some applications array will be a heavier solutions. Okay. Next is more complex. Okay. When you are going for a phased array kind of thing. Okay. Next is array antennas. What is happening in array antennas? So there are two things. One is we have a plenty of array of elements, right? The array term came from this, array of elements. Okay, that is brought together in with a particular spacing, and it is excited with some amplitude and phase. So let's say you have, for example, element pattern like this, dipole pattern, 8 pattern, right? Then you have a array factor. Okay, array factor is nothing but we will see later. So array factor, when you multiply these two, element pattern with the array factor, then you will get this total feed pattern here. So you can control, see, leave alone this element pattern. By controlling this array factor, okay, I can able to control the radiation pattern, the total radiation pattern. That is the key here. Okay, one is, so see, element pattern now you cannot do beyond certain things. Once you finalize the element, that's all gone. Okay, next what you can do, you can play with this array factor. So once you are playing with the array factor, you can even you can steer like this, you can concentrate like this, for example, by enhancing the spacing, and by applying the appropriate weights and the amplitudes, and you can control this beam. Okay, by controlling this one, I can control the total radiation pattern. That's what is the layman language definition of this pattern multiplication, basically. Okay, so now we move on to n element array. Okay, so here n element array. So now our topic is like on the uniform array, right? So uniform amplitude and spacing. So uniform array means what? So uniform array means it has an identical elements. That is first of all that it should be applicable. And the second is identical magnitude, which means whatever I am exciting, so that should be identical. Okay, and then you have each with a progressive phase shift. Progressive phase shift means, so the difference between the each element, right? The phase should be progressive, so that you can convert the pattern like this. Okay, so it should be identical elements and identical magnitude, and each with the progressive phase shift, so that you can you can get this beam kind of thing, like these kind of beams. Okay. Okay. Next, so array factor can be, see, in theoretical way, what we consider is array factor will be can be obtained by, in theory. What we do is we consider the element as a point source. Okay, point source means we always point source means it will always radiate in all direction as equal. Okay, equally radiate in all directions, but you can modify that by, for example, element, by considering element as a dipole. Okay, even you can custom radiation pattern also you can involve in this element as well as an element. While if you look at the MATLAB code, any of the phased array and those things, they always consider as a point source most of the time, but in some of the cases they consider as a dipole. Okay, the element as a dipole which has a 8 pattern. Okay. Next, we have, this is what is in the array pictorial representation. For example, you can see here that 1, 2, 3 or 2 n elements. It has a spacing of, for example, D. It has a spacing between the element is D, and the theta is nothing but your, for example, if this is the target direction. For example, where I have to project my beam, this is the target direction. So what angle it's subtend along with this axis, that is calculated over here. D cos theta, whatever is mentioned over here is to calculate this, for example, phase offset, basically. So what phase offset I'm having with respect to 1, 2 with respect to 1, and 3 with respect to 1 and 2, 4 with respect to 3 and 4. So that offset we are calculating using this D cos theta, basically. Okay. And if you for example, array factor will be 1 is here, and then when you are moving away, then you have for example 1 plus j kd cos theta plus beta. Beta is nothing but your uh, the phase to be applied, and until this, then you are I think some series you apply here, and then you will, I forgot actually. Okay, then you are finding out this array factor. The key point to be noted here is that see, the beta is the phase constant, and theta is over here, right? The kd cos theta, what it refers kd, why we are using kd cos theta? Why? Because see, um, let me go to this one. Okay, I don't know whether editing option is available. So, kd cos theta, why we are going, just we'll just have a quick glance of it, and you can see here, this is the one element, this we have as another element. Okay, then see, with respect to, this is the where I am observing this radiation pattern. Okay, this is the one distance, and this is the another distance, right? So this is this distance, for example, let's say x1, this is, we can say as s2. Okay, x1 is higher than x2. Okay, so in layman language, okay, so the signal that reach from here to here, here to here, the time taken by these, the signal to reach over here by these two, from these two elements is different, right? Because the x1, the signal come from x1, travel through x1 distance will have a higher time than it will reach in late than this x2. Okay, so what we have to do is, for example, this offset, how I am going to compensate for. Okay, so that's what this was the theta, right? If you just calculate like this, the cos theta will be your adjacent divided by this value. Okay, the adjacent, that d cos theta will be, sorry, my cos theta will be d by that particular offset value. Okay, let's say x. Okay, and then adjacent divided by no, this is hypotenuse, right? Opposite divided by x by d, it will be, so the x will be actually d cos theta. Okay, that's why that d cos theta term comes. And also we have added one more term called k. Okay, so let's say why we are adding k, that we'll discuss, and then we'll move forward. So d cos theta, let's say, so d is for example 0.5 lambda. Okay, so when you theta may be for example cos 30 or something like that. So you are having for example 0.4 lambda. Okay, 0.4 lambda offset you are having the in terms of distance between these two points. Okay, so now I have to find out what phase offset I have to give. Means I may expect from this. See, as an observer, what phase offset I can get from these two elements, that I have to find out, right? That's why I'm multiplying by k. K is nothing but your 2 pi by lambda. Okay, so lambda get cancelled. Then 2 pi into 2 into 0.4, I think 0.8. Okay, 0.8 into pi. So this is the phase I'm getting between these two one. So that's why we are always we are using this kd cos theta. Okay, that's only point you have to note down. Then so once you find out this array factor, then this is for the n element basically. Now what we do is we are applying this um, uh, this is kind of simple actually it's a math. You have to rearrange this, you have to take out this e power j z, and then find out this one. Okay, and you have, for example, see, this is the array factor for the basically for the n element array, the final normalized one. Okay, this is the normalized one. So this array factor, no, So we have to start from two element and then element. So then only we'll understand. I'm just giving you just brief introduction about this array factor. Then we'll move forward. Okay. And here you can see that so the array factor has a term called as psi. Okay, and then sin psi and divided by sin 1/2. So here the n is nothing but your total number of elements. That's why we are calling it as normalized array factor. Okay, normalized array factor. Here we have done some kind of simplification. How? Because when your n is more, then what will happen? Like that, we consider the then we have simplified this equation. Okay, and I think this will also well valid because the sin psi by 2, if it is too low, then we can simply call it as n psi by 2, like that. Okay, this psi is nothing but your this is the equation for the psi kd cos theta plus beta. Okay, now the point here is, now I have to find out, so where should be my maxima? So maxima will occur by putting making this psi as 0. That is the key point here. Maxima means what? So let's say this is the element pattern, this is the array factor, this is the particular this is the maxima. Basically this is the maxima we are having. Maxima means where I am concentrating more power to a particular direction, which is main lobe basically. So if I want to get maxima over here, maxima out of this array factor, what I have to do? I have to make this value as 0. Okay. Sorry. From this expression, if I want to get a maximum value, what I have to do? I have to apply 0 over here, so that sin 0 by sin 0, it will be an infinite value. Okay. That is what is the condition we always use for calculating this phase value, beta value, and then find out which direction this broadside array, Endfire array, and so on. Okay. Next comes linear array. Has, for example, broadside radiation pattern, ordinary Endfire array, phased array, this one. So the difference between broadside array and Endfire array is that let's say, see, this is the dipole. Okay, consider this as a dipole. So if your radiation pattern is this direction, okay, which is 90°, okay, perpendicular to this antenna direction, then it is called as broadside array. Then if your direction radiation pattern is this one, in this direction, then it is called as Endfire array. Okay, Endfire array. End kind of the name itself says end fire array, kind of fire. It is radiating the in that particular direction. Okay, so broadside array, Endfire array. So these are all the two kind of arrays. These material, no, I have adapted from Balanis lecture notes. Okay, so theta m is 90. Okay, where theta m is which direction you are pointing the beams. Mostly dipole will have this kind of a broadside array, and for example, Endfire array example is, for example, Yagi Uda, and some of the antennas are available for the Endfire array as well. Vivaldi antennas and so on. Okay, and phased array scanning angle. This is the phased array. So just you have to scan the angle between the 0 to 180, but it will not happen in reality. Okay, so you have to just it's kind of scanning array. Next is the Endfire array itself, Endfire array itself, ordinary, and also Hansen, Woodyard, many more, few more are also available. Okay, there you will have some kind of conditions for the array factor, the calculating these values. So this is a kind of on top of this Endfire array, you have a Hansen Woodyard Endfire array will have some kind of logical, some kind of conditions. He applied some condition to obtain the, for example, low side lobe level and enhance the gain. That's the Hansen Woodyard's contribution on top of this Endfire array. That is the one. Next, to give you an overview, that broadside array, we mentioned that sometime back. We mentioned that though the angle of radiation direction, the radiation direction is, sorry, the angle of or the radiation is theta is equal to 90° basically. Okay, theta is equal to 90°. So when you apply this theta equal to 90° over here, okay, so then what happens? This will become 0, then beta will equal to 0. That is the condition. So beta is equal to 0. Then what happens is Next is d is equal to n lambda. The features is that, see, in order to avoid the grating loops, that is the idea here. And you can see here that if you want to avoid this n lambda case, then 0 to n lambda, then you are having, finally, if you simplify this equation, and then you will find out this. So the here theta you can apply as for example, beta equal to 0 means it will be, when you apply in psi equation, no, when you apply this beta as 0, then you will have a kd cos theta. And why we are having this n lambda case? Okay, so in order to avoid this n lambda case, 1 2 3 like that. Okay, so we are avoiding that, and then finding mentioning it as 2 pi into n cos theta. So by substituting d equal to n lambda, what will happen? K you substitute as a 2 pi by lambda. Lambda get cancelled. Then you will have a 2 pi n cos theta. Okay. Then theta can be, it can be a 0 or 180, whatever maybe. And then you will find out when once we find out psi is equal to plus minus 2 pi n. It just most of the time we play with this, find out the beta, and then substituting this psi equation, and then the simplified equation is given in the book. Okay, for the broadside array and various conditions as well. For example, if we want to generate a null, then what is the equation? And null equation, first side lobe level beam width, first null beam width, half bar beam width, or for all the stuff, the equations are given in the book. Okay. And this is what I was telling. So broadside array, you can see here that the antenna pointing towards the z direction, but your pattern is on the xy plane basically. Okay, and here you can see that it is a very broad pattern basically. Okay, why? Because see, you are having lambda by 4 as the spacing, and the number of element is 10. To have an idea that, see, you can see here that the same number of elements I'm going to use. Okay, same number of elements for a broadside array. What is the condition? Beta equal to 0 because theta is 90. Okay, now same conditions here. You can see two kind of patterns are available. So here, just to show you that when you are increasing the spacing, for example, d equal to lambda, what is happening to the pattern, and also d equal to lambda by 4, what is happening to the pattern? That's what I want like to show here. You can see here that when d is equal to lambda, okay, lambda by 4, okay, you can see here that it is a broad beam. Okay, you can see here that it's a broad beam. Okay, but whereas when you look at this d equal to lambda, what is happening? You are getting a narrow beam. Okay, so which means, so here what we are inferring from this radiation pattern, when you are increasing the, see, same 10 elements, okay, same 10 elements, if you are having 10 lambda by 4, let's say 10, okay, lambda by 4 equal 10 centimeter, let's say 10 centimeter, 10 into 10, 100 centimeter is the array size. Okay, when you are putting lambda itself, okay, it's a 40, right? So here the first case we are taking it as d equal to lambda by 4, which is a 10 centimeter, let's say. Okay, 10 centimeter. So 10 into 10, 100 centimeter. Okay, now next case what I'm taking, d equal to lambda, which means 40 centimeter basically. Okay, so 40 centimeter means 40 into 110, 400 centimeter. So what I'm getting here over here from this, see, this dimension, lambda as a spacing, and from by looking at this beam width, what we are inferring there is that, so when your array size is increasing, okay, what is happening? The beam is getting narrowed down. Okay, that is the inverse relationship. When your beam width want to be narrow, then you have to increase the array size. There are many other methods, but straightforward method is this. You have to increase the array, which means what? You have to increase the number of elements, okay, or increase the spacing. Okay, next is, well, when you cannot increase the spacing as you want, like, okay, you because the moment you start increasing the lambda beyond lambda, then what will happen is your grating lobes start shooting up. Okay, and when you are having, if you want to have a broad beam, then you need to have a smaller spacing. That is the inference we are getting over here. One more inference is that, so when you are having narrow beam, okay, narrow beam means it will focus, or it will travel through longer distance, because it is having higher gain. So gain and beam widths are inversely proportional. Gain and beam widths are inversely proportional, which means for narrow beam you will have a higher gain, and for a broad beam you will have a low gain. Okay, that is the one. I will tell you in a short time, analogy as well. So for narrow beam, it will be a high gain. When a broad beam, you will have a low gain. Okay. If you want to correlate with this spacing with the gain, when you are having lower spacing, you will have a lower gain, broader beam. Okay. When you are having higher spacing, you will have a narrower beam, but higher gain. Okay. That is the logic you are getting from this particular plot. Okay. Next, I was telling you, right? So broader beam means lower gain, narrow beam means larger gain. So what have we visualized it in our life, day-to-day life? Yes, we have visualized it by, for example, battery, torchlight, right? Torchlight. When you are having high power torchlight, LED torchlight, okay, with the, you see, where you might have used maybe your 30, 35 plus, okay, maybe some of you maybe 35 plus. In olden days, we use one torchlight, which will have a small bulb and you will have a reflector in it. Okay, when you remove that reflector, that the torchlight will not be visible for the short, will be visible for very shorter distance, maybe 2 or 3 meters or 5 meters, right? The moment you connect this reflector on it, then it will focus to particular, around 100 meter basically. So that is the logic here there. So what is happening when you are having LED alone, that a bulb alone, you are having broader beam, therefore lower gain. So the vicinity is very within 2 or 3 meters or 5 meters. Okay. The moment you connect this parabolic reflector on it, okay, torch light, for maybe some of you maybe younger people, okay, torch light. Let's see if I get it. This one, okay. Okay. So now LED came into picture. This is the one. Okay. So this is the one I was telling us. For example, this is the one as a parabolic reflector, a reflector basically, reflector. And you see, this is the reflector, and this is having bulb. Okay. Just a short analogy. Okay. So the moment you connect that reflector, you are having a larger distance. That is where you have to correlate with the gain. So when you are having higher gain, you will have a longer distance communication. When you are having lower gain, you are having shorter distance communication. Example, a simpler example is you are using for telecommunication. You are using moderate gain antennas. That's why it's covering up to 7 kilometer or something like that, more less than 3 kilometer or 4 kilometer like that. Okay, but when you are having in the satellite communication, right? Satellite communication, we are, signal is traveling for such a long distance, right? That's why we are always using parabolic reflector or array antennas or, reflector array antennas, something like that. Because, we need to have a gain of, for example, 30 to 40 dBi gain in order to, and also with the supported RF lineup to reach that particular larger distance. This is what we were discussing some time ago. When you are having the spacing is less than lambda, then you will not have grating lobes. So what is grating lobes? You will see multiple maximas. So why it is redundant over here? When you start seeing multiple lobes, what will happen is, for example, your power is getting wasted in two different directions. Though user is not there in particular direction, you are wasting your power. In if I say in defense terms, so your, for example, for example, your radar is, for example, some flight is tracking your radar, okay, capturing your radar and then moving like this, okay. The moment it sees grating lobes, it will confuse between these lobes. So because both will look like a same lobe, right? Though the signal passing will happen, but sometimes it may confused. That's why the grating lobe should be avoided. Okay, because we cannot avoid beyond certain range, but we have to avoid that. Okay. Next is Endfire array. As I mentioned, either you transmit in the, for example, if it is a z direction like this, either you radiate in this particular direction or 180 means just exactly opposite direction. Okay, so toward theta equal to 0, if you substitute that theta equal to 0 over here, then what happens is theta equal to 0, then beta will become minus kd. Okay, when you substitute theta is equal to 180, the beta will become plus kd. Okay, so you just substitute and then we will get these values. Okay, and we'll have for example, similar example over here, in 10 elements, lambda by 4, and then beta equal to kd. What will happen? That's what is just a minus pi by 2 plus pi by 2, and maximum at 0 degree. This is the case for the maximum at 0 degree. This is the case at maximum at theta is equal to 180 degree. Okay, so we'll just look at this pattern. Okay, so here you can see this is the antenna. Okay, this is the antenna. I'd say this is the antenna. Here they have considered this is the direction. So the radiation pattern in this particular direction. Okay, and theta equal to 0. Whereas in this one, it is towards the uh, bottom direction, which is 180 degree. Next, you have, for example, similar kind of example over here. You can see here that when you are applying plus beta kd, which is theta direction, which is the dotted line, minus theta kd is for the theta equal to 0 condition. The dotted line over here, and when you are having beta is equal to plus beta plus kd. Okay, so that is for the 180 degree. This is the one. Okay, just to show you both plots in the same one. That's the only thing. Okay, so here as I mentioned in the first slide, that you can identify, okay, which direction my antenna is radiating. For example, sometime what happens is, if you are having slight variation in your design, okay, some kind of malfunction in your design, what will happen is, see, you will see simulation tool, you will see perfectly it will be radiating in broadside direction, in 0 degree. Okay, but when you fabricate it, so you cannot ensure everywhere the tolerance, right? I mean, some milling machine may have some fault, or many things may happen. What happens is, instead of 0 degree, I may have a beam squint. We call it as beam squint. This maxima may shift towards this particular direction. Okay, so that we can clearly see over in this polar plot. That's why we always prefer to have a polar plot where we can see number of side lobes, back lobes, and how much relative value and all that stuff. Okay. So next we will move on to planar arrays. So so far we have seen linear arrays. Sorry, I forgot to tell that. So linear array is the one which will have a number of elements in the one direction. That's all, one axis. Let's say x, either x or y. Okay. But when you look at this planar arrays, we'll have elements in the both xy plane itself. Okay, xy plane. Okay, so linear array is basically a one-dimensional one. Okay, so here what we get is, it will scan the beam only in one plane. Okay, whereas to scan the beam in any direction that we want, then you have to obviously go for two-dimensional array geometries. And so it can be, see, two-dimensional means it can be a circular fashion or planar one, which can be a rectangular one or square one, cubical one, cylindrical one, anything. It can be spherical surfaces. So in order to understand this one-dimensional, just let me go back to this. So this is the one, okay, where you have an array. Okay, so as we mentioned, this is the, let's say, x-axis. This is y-axis. Okay, y-axis. This is z-axis. Okay, z-axis. As we mentioned sometime before, that when you are having number of elements as high, then you will have a narrow beam in this xz direction. Okay, but in y-axis you don't have any number of elements, only single element. So you will have a broad beam width like this, very broad beam width like this. In the, I don't know, I'm not a good drawer. You can see here. So in y-axis, if you look at this y-axis, it will have a very broad beam like this. Okay, but in x-axis, along x-axis, xz plane, you can sweep the beams. For example, like this, like this, like this, like this. You can steer the beam, but in y-axis you cannot do anything because you have only one element. If you look at from the y-axis perspective, okay. So that is the beauty of linear array. Okay, but it's where you need to only have one-dimensional scanning. There we can use this kind of thing. But best example is the aerodrome. Okay, aerodrome. Why we are using this? Because see, it has to horizontally rotate, horizontally scan the flights that are being landed. Okay, you don't want to see elevation. You cannot see elevation. So elevation you can see for the certain distance, not for the not certain direction, not above that. So maybe 5 or 10 meters. That's all. So more than that, you don't have to look at it. You have to horizontally scan how many flights are being landed on that stuff. So that point of time, you can use this linear array, for example, in the aerodrome. Okay. And when you are looking at the planar array, let's say square array, okay, you have multiple elements like this. Okay, you have a multiple element like this. Okay, so I can control the beams in both the direction. So it should be equal element, uniform element. Sorry, so by mistake. Okay, so I can control the beams in the both the directions. So like this, or in elevation as well, I can control. That is what. So both the horizontal as well as vertical. This is what we are using in this massive MIMO basically. Okay, massive MIMO, or for example, face tracking radar. Many radars they use this kind of stuff. Okay, planar arrays. So this is the linear array. Just we have seen this, and you can see here this is the linear array in one axis. So here you will have an narrow beam, but in along Y you will have broad beam basically. Okay. Next, you have planar array where you can have a beam can be controlled in both axes along throughout the XY plane. That's the only thing. And the array factor for this is the one, like after simplifying. See here, the elements are in both the direction, right? So that's why it's a simplified one. Next, we will see that. Yeah. Now, the point to be noted here is that for z-axis, it's fine. KD cos theta is fine. But if you closely look at this xy, okay, xy, we can see that there is one more term called cos phi and sin phi came into picture. Okay, why it is? Because we are considering the whole plane, xy plane. Okay, so that's why it is kind of it's a rectangular to spherical coordinate conversion. Okay, that is what they have done over here. Sin theta, cos phi. So theta, where is theta? This is the theta. So how I see theta means how much angle it's subtended from the z-axis, and the phi is nothing but your how much angle it is subtending in the xy plane basically. This is theta is subtended in the either with respect to xy and z, whereas theta phi is nothing but your how much angle it is getting subtended in the phi direction. XY plane, in the xy plane. Okay, that is what is the. That's why we have both the terms sin theta, cos phi. That we need to note. Okay. And for x-axis, we have sin theta cos phi, and for y-axis, we have sin theta sin phi, because sin is y is nothing but your 90 degree. So if you take this 90 degree one is sin theta, sin phi basically. Yeah. Then you have a uniform planar array where you can see that here uniform means what is uniform? Uniform is amplitude is constant. That is the assumption, right? You are not going to excite individual element with a different excitation. So what I'm doing here, so I'm taking out this. So that is the the common term we have. For example, a uniform amplitude, that we take out that, and then we simplify this equation. Here, this is for the, for example, along x, okay, number of element is m. Along y, we have a number of element is n. We go back to this one. So you can see here, along x, you have a number of element is m. Along y, you have a number of element is m. Okay, that is what we have to get info from here. Sin theta cos phi is for the x-axis. Sin theta sin phi is for the y-axis. Okay, beta x, beta y. That's it. Next, so array factor is uniform array means we mentioned in the first, second, third slide itself that it will have a equal. All elements are uniform, means similar elements, same element, and uniform amplitude and excitation basically, amplitude and phase. Okay. So therefore, when you substitute all this assumption over in the array equation, array factor equation, then you will you will converge to this equation basically, where you can see that sin m by 2 by six, where you can see that, see, in one dimensional we had only this equation. Okay, but two dimensional you have one more term multiplied. That's it. Okay. Okay. So say in layman language, you can see that in one dimensional we had only this term. Okay. Whereas for the planar array, we have this another one as well. Okay, that is the inference we get from this equation. And obviously, see, maxima again. When I mentioned maxima 0, psi x should be either 0 or 360 or 720 or something like that. Okay, because then only we will get the maximum value, right? So that's why in order to get the maximum value, so psi x would to be 0, 0, 2 pi, 2 pi, 4 pi, like that, right? So that's what is mentioned over here. M can be 0, 1, 2, like that. Okay, so this is the maxima condition for psi x as well as the psi y. Now, let us look at this, some of the plots. So how the beam width is getting varied over here. I think we mentioned in the previous slides, but we will just look at in the pictorial representation. Here, three-dimensional antenna pattern of the, so far, one more thing I wanted to show you that for linear array. So, hello? Hello? Hello, madam?
Sir,
Madam?
yes, sir, yes, sir.
Okay, sorry. Was in between. Okay.
Okay.
So planar array, yeah, planar array, sorry. Okay, planar array has, radiation pattern, like just look at this. So the spacing between the elements in the x-axis and y-axis are same, that is lambda by 4, and beta x, beta y equal to 0. Okay. How it comes? Because, you can see here that, for example, if I apply the maxima condition, it will be 0. Okay. And let's say that's for the broadside, what will happen? Beta y equal to 0. So why we are applying here? Because if cos phi is equal to 0, then what will happen? The entire term will go to beta x will become 0, and and we can see that then theta naught is equal to, let's say, for example, sorry, this is the condition. The dx dy equal to lambda by 4, beta x equal to 0. Why? Because theta not equal to 0. Okay, that's what we are considering over here. And then number of element is 5. So for just to closely look at this, we have lambda by 4 as the spacing, and the number of element as 5. You are getting very broad beam like this. Okay, very broad beam like this. When you look at this next example, okay, exactly double. Okay, so your array size is exactly getting doubled. Okay, same 5 number of elements, same condition, but the array size is getting exactly doubled. Okay, that's why you can see that the beam is almost one half of that. Correct. Beam width is almost one half of this. One half of this. So that's what we can see, witness. So again, this I reiterate that when you increase the size or increase the spacing, what will happen is beam width will get narrowed down. Therefore, the gain increases. That is the observation we are getting over here. I think we have half an hour, so we can definitely cover. Okay, design procedure. It can be a linear array or planar array. Okay, then the design procedure should be it is common only. So now first we need to decide. So which direction my radiation pattern should be? Okay, either it can be broadside or Endfire array or Hansen Woodyard or ordinary. This we need to decide. Okay, first before we go for the which direction I want radiation. Okay, which direction I want to focus my energy or focus my power. That we need to find out. For example, so some application, right? You need to have an Endfire kind of thing, and some applications, for example, mobile applications, it is a critical one, typical one. You will have a broadside one, and some antennas need to have a upper one like that. So many requirements will be there. So some of the in flight itself, we will have Endfire one, broadside one. So it depends upon the application use cases. We have this. First, we need to decide which direction I want to radiate my which direction I want to focus my energy or radiate my power. Next is number of elements. Then you have to design. See number of elements. How you decide? So how you decide based on the directivity. Okay, you can be both the ways. So it can be, for example, number of elements you can decide because you will be given space. Then you can decide the number of elements, spacing between the elements, Okay, spacing between the elements and the array size will dictate you number of elements. Then excitation type, amplitude and phase, what excitation you are going to have, either uniform or non-uniform or anything else. Then half power beamwidth, what you are expecting from this. So once you get this numbers right, number of elements, spacing between the elements, excitation, amplitude, and then all that stuff, you may be able to roughly calculate this one, half power beamwidth, how much, and therefore half power beamwidth indirectly we are calculating what we are calculating, directivity, then side lobe level. Okay, so all this stuff will be calculated based on this. Okay, so you can go in reverse way also. Okay, some of the application, no, you will go in reverse way. I need this much gain. That's it. In telecom mandal, we will have that kind of requirement only. I need this much beam width, this much steering angle, this much directivity, this much side lobe level. Yeah, now you design. You have this much space, very small space like this. Okay, now you design one antenna for me. Okay, then you have to go back and reflect on us, and then which element going to be used, a number, how many number of elements accommodate with the appropriate spacing, and what excitation I have to give in order to meet these requirements. So that's how the design will go out. Okay. Now here, if you look at this one, so when I mentioned this excitation, right? So look at this. So that when you are having uniform excitation, you will have a side lobe as well as, obviously you will have a side lobe. Okay, with a certain power level, for example 13.5 dB is the in your exciting with the uniform, then you will get the minus 13.5 as minus 13 dB side lobe level. Okay, you will have a pattern like this. So if you this is the case. Okay, the second case, what I'm doing is, see, you have an array of elements. Okay. Okay, let me mention. So here, the second case is nothing but you have an array of elements. Okay. Um, like this. Okay. Now, so I have to decide. So which direction I want my beam to be, directed. So what I have to do is, see, either I want beam to be in this direction or this direction or this direction. Accordingly, I have to excite. Okay. In this case, what they have done is, I want beam in this direction. Therefore, I have to excite only the edge elements. Okay, I have to excite only the edge elements. Center, I'm not exciting anymore. Okay, that is why you can see here that U shape here, which means amplitude is high at amplitude excitation. Amplitude is high at edge of the elements. Okay, edge of this z-axis. No, if you draw here, this is the z-axis. Let's say z-axis. Excitation amplitude is high over here, where in this, when you're approaching center, you are having almost zero. Okay, that's why you are getting null over here, almost side lobe level, but null over here in the center. You are getting this kind of very strong, radiation pattern over here. Similarly, on the right, third case, where what we are doing, the similar array. So, kind of array elements are there. Okay, array of elements are there. Okay, array elements. Okay. So this kind of pattern, right? This is the z direction. Okay. The problem, see here, what I'm doing, my beam to be here in this direction means that's why I'm doing. I'm exciting more over here rather than in the edge. So what is happening? I'm giving tapering. We call it as tapering, amplitude tapering. Okay. Tapering means the moment you move out of the center, you will start decreasing the amplitude levels. For example, if let's say it is 1. It may be 0.1. Let's say it's 0.1. Okay. So it will gradually decrease from 1 to 0.1. Okay. So therefore, I can steer the beam. I can, project the beam in this particular direction. Okay. So here, in this case, the side lobe level is fixed. Okay. But theoretically, it will be fixed. But, ideally, practically, you may achieve around this. My gain is maximum. Here, the thing is, side lobe level is very high. Because you are getting only side lobe level, but in some application you want pattern like this only. So it can be a side lobe level. We can say, see, this is the actually here our focus is only in this direction. That's why here side lobe level is very high, Main lobe is very small over here. Main lobe is very small over here. Side lobe level is very high. But in some applications, we want this kind of pattern only. That's why we have this kind of thing. Edges are strongly illuminated than center. Therefore, more side lobes and the gain is minimum. Okay. Whereas here, side lobe level is very low because I'm not exciting edge elements anymore, right? Only these central elements, right? Gain is intermediate. Then you can adjust the side lobes by controlling this taper. You can able to adjust the side lobe levels. Okay. Now, so far we have seen. Let me quickly cover and go through the. I mean, say, quickly rush. Some 2-3 minutes I spent on it. So far, what we have covered. We started with the preliminaries. Then we covered up parameters, and then pattern, how to look at the how to interpret the plots, and then we started with the arrays. Definitions and pattern multiplications, and also the various different arrays what we see in nature and also in other domain like light and sound domain, sound waves. And then we have seen some few examples of arrays. Then we started with the n element array. There we have discussed about what is uniform array, identical elements, identical amplitude, and identical phase, like that, and so on. And how the array factor, how to interpret the array factor. So where we get the maxima, and how we can, how we can differentiate the patterns in terms of, for example, it can be a broadside array, Endfire array, like that. So, and then we move on to broadside array. So, a few examples and how to interpret the by looking at the pattern, which one is having higher gain and which one is having lower gain. By looking at the array size, which one will give me higher narrow beam width, which one will give me higher broad beam width. That we can understand by looking at the dimension of the array and also the spacing between the elements, or element size, and so on. That we have seen. We have interpreted a few results, and then we have seen some examples for the broadside array and the Endfire array. Then we came into planar array. Why we go for planar array rather than this linear array? Because we need to steer the beam in two-dimensional fashion, not in the only one axis. That's why we go for this. And also you have advantage of narrow beam in both axes, both x and y axis, right? The entire experiment, so that your radiation can be controlled in a particular direction, right? But whereas in the linear array, you will have a narrow beam in one particular direction, one particular axis. The other axis, you will have a broader beam because you don't have any elements. Only one element you have. If you look at from the y-axis side, you will see only one element. But if you look at from the x-axis side, you will see plenty of elements, right? Some of the applications like aerodrome and massive MIMO that we have discussed. And last, we have covered this design procedure and some examples we have seen for the planar array radiation pattern, then design procedure, and we have seen these excitations. Now we are moving to the another application of an array like a phased array. Okay, so why I'm covering this? Because it will be a preliminary for the massive MIMO basically. That's why. So now you can see here that how do I achieve the phased array or scanning array? Okay, so the term is when do I achieve this maxima? So maxima is 0 degree. When I have a psi as 0, then I will get the maxima. That is the thumb rule we have. So when psi is equal to 0, I will get the maxima in particular direction, right? Now, so when if you substitute that, beta is equal to what will happen? Minus kd cos theta naught. Theta naught is variable over here. So here theta naught, what I can do? I can vary from between 0 to 180. 0 to 180. So therefore, by varying this value, what I'm doing? I'm controlling this radiation pattern in each direction, right? We are scanning the array, beam scanning. Okay, we are doing beam scanning. So therefore, by controlling, so indirectly what we are doing, see theta naught, I want radiation in this particular direction. So by mentioning in the theta, indirectly what I'm getting. So by controlling the beta, what I can obtain is a maximum radiation can be splintered in any desired direction to form a scanning array. Okay. So by controlling theta, I need beam to be directed in particular direction, 30 degree, 40 degree, 180 degree, or whatever it may be. So indirectly, what I have to do is by controlling beta, because beta is the one associated with this theta, right? Theta naught, right? So by controlling beta, I can able to control the beam scanning basically. This is the principle of electronic scanning phased array operation. Okay. So next, why we go for this? So here the progressive phase shift, right? Beta progressive phase shift keep on changing for each case. Progressive phase shift keep on changing for each case theta naught. For each theta naught, progressive phase shift get changing. Here we can do many scanning in terms of electronic. We can do frequency scanning. We call it as analog scanning. Then we have phase scanning. Okay. Next we have a time delay scanning. Just a moment. Am I audible?
Yes, sir, audible, sir.
Okay, thank you. So frequency scanning, phase scanning, time delay scanning. So time delay is almost similar to phase one. Okay, phase change can be achieved by switching the different length of transmission path. Okay, so transmission path means so I can control the transmission path length by putting the diodes in between or capacitor in between. So I can switch on the particular diodes, or transistor in a particular time so that it can be connected. Transmission line be connected and lengthy. So that way we can able to control this. Then beam switching. Okay. Next is here you see some of the phase shifter we can use to control this phased array basically. Ferrite phase shifter. Another one is diode phase shifter. So ferrite phase shifter, no, it is by changing the amount of current that is going to the, so magnetic. So by controlling the current, the magnetic field within the ferrite I can change. Therefore, the phase shift that it introduced by ferrite, it will get changed. That way we can able to achieve this phase shifter. So why I'm talking about these kind of phase shifters and all that stuff, because by controlling the excitation of the element, I can steer the beam. That is the obvious idea here. Next is diode phase shifter. Here we have to vary the bias voltage. Okay, or digital command. Now digital phase shifters are available. Okay, digital command you can able to convert the. You can see here bias voltage you can do. Otherwise, what you can do by having enabling digital command, then it will be converted to digital to analog form. Okay, then it will be fed to diode. Therefore, I can achieve this phase shift. Okay. And this is kind of scanning. You can see this is the the two kind of different beams we are achieving over here. And if you want to tell in implementation perspective, layman perspective, implementation perspective, so how it works is, let me show you one example, not example, just some illustration with the help of Butler matrix. So you have a Butler matrix like this. Okay, you have directional coupler and also crossovers and phase shifter over here. Okay, these 4 ports are 4 input, 4 output. Output of the Butler matrix is connected to this antenna elements basically. Okay, now this is the static one. Okay, Butler matrix is static one. When you excite, see this is the directional coupler, phase shifter and crossover and phase shifter. When you excite here, I will get a beam like this. This is fixed. The moment you excite here, I will get a beam like this. The moment I excite here, I will get a beam like this. The moment I excite here, I will get a beam like this. Okay. The moment I excite here, I will get a beam this. This is the kind of manual one. Okay. So here we cannot change. We can only change when by placing this phase shifter. I can change it to digital phase shifter. By controlling this digital phase shift, I can even tweak this direction as well. So though I see, for example, this direction I'm getting now. Okay. So now I want to reconfigure it. So I don't want like this. I want to reconfigure it, but Butler matrix does not allow me that. But what I can do, the solution is, what I can do is, I can use digital phase shifter in place of analog phase shifter. Analog phase shifter will give you fixed phase shift, right? I'm going for dynamically changing phase shifter. Therefore, what I can do, I can tweak this direction, because this phase shifter plays a major role here, right? Playing a major role here. Therefore, by controlling indirectly, I'm controlling this excitation phase to steer the beam here and there. This is the approach you can follow this for the phased array. So when I do this, what will happen? This kind of scanning I can do, correct? So this kind of scanning I can do. Okay. So by controlling this, so this is a simpler example, but you have a much more complex algorithms are there, complex implementations are there, where you can achieve whatever way you want. Okay. Now see in phased array, right? You have a digital. See the beamforming will have a two kind of beamforming technique. One is analog beamforming, which we call it as frequency-based beamforming. Digital beamforming, which is time domain beamforming. Analog beamforming is frequency domain beamforming, and we have a hybrid beamforming. Okay, let me point out a few advantages, disadvantages over there. Okay, in each category. Analog beamforming, the advantage here is that you have baseband processing. Okay, your data streams are coming over here and processed by the baseband chips, FPGAs. Then it is giving to digital to analog conversion, and then it will go into RF lineup. Okay, here what we are doing, you are splitting into multiple one. When you have only single baseband, then you are giving to multiple thing. Here, what you are doing is analog phase shifter. You can see here, analog phase shifter you have. By controlling this, you can steer the beam here and there, wherever you want. But now, digital beamforming, what I'm doing is like, here the disadvantage is that if you want to change the frequency, right, frequency band, right, or for example, if you want to change the numerology, in 5G, we call it as numerology, subcarrier spacing. There is one term called subcarrier spacing. You can explore, Google it and explore it. So if I want to change that, then I have to replicate one more. Okay, I cannot do with this. But whereas here, I can do it. So you have each data streams will be processed by each individual digital baseband processing unit, then RF chain, then you have antenna, right? So here the disadvantage is that you need to have multiple baseband chips, okay, multiple baseband processing units. Okay, therefore resource utilization will go up. Therefore, this is not viable one in some sense. Okay, but you have a much more flexibilities. You can apply any frequency that you want. You can apply any modulation scheme that you want. You can apply any subcarrier spacing that you want. Therefore, each has its own advantage. It is having low cost solution, but it is a high cost solution, but there is no flexibility over here, but flexibility is there. If you want to, have a flexibility as well as the low cost solution, I can go for this hybrid solution. Okay, where you can see that each baseband processing having RF chain, then each RF chain is connected to few elements. Here till now, I'm doing digital beamforming, which is each individual RF chain will have. Then each RF chain will be converted into multiple one by in the analog beamforming network over here. Okay. So this is same fundas, like, for example, 2 pi lambda to a KD cos this KD sin theta only. Okay. Here they call it KD sin theta, but in the other diagram it will be called KD cos theta. You can see here that the same funda, so phase shifters, attenuators, just to control the power amplitude basically. Attenuator is for the controlling amplitude, phase shifter is for the controlling phase. That is being excited to each individual elements. Okay. To far field. I can control the beam in any direction that I want. Right. So similarly, you can see here if I del phi go to 0, what will happening, del phi 90, what's happening. Okay. And this was actually, I don't know what was happened to this animation. It was just steering like this and like this. Okay. And next, I have just quickly go through about this. I think hope you might have seen this before. So antenna evolution is 1G. It was by kind of big elements. I will tell you why I'm covering this. 3G, 4G, 5G. Okay. So now the point here is, here it is one element we had. Antenna element is one, spiral antenna or loop antenna or helical antenna, like that. We had this one. There we did not have much challenge, right? The moment you come to 5G or 4G, you talk in terms of array, phased array as well, as MIMO, massive MIMO array as well. But though they are not using in millimeter wave, FR1, FR2 we have. So in FR2, though it is handsets, some handsets are supporting in abroad, but not here. So there you talk in terms of array. So when moment you talk in terms of array, then your excitation involved, how steering the beam is involved, many things is involved. So that is the complexity we are seeing now. Next is in base station side, what is happening? 2G, we have a single direction antenna, that's all. You have to steer the beam in a broad beam, that's all. But in 3G, we had some smartness, like we can control the electrical tilting through remote. And in 5G or 4G, 4G LTE advanced onwards, you are seeing some kind of massive MIMO radio, right? Where you can control the beams in any direction that you want, so that the SNR is getting increased, and also user is getting, exclusively, pointed with the beams, so that, SNR is getting increased, and you are getting a lot more flexibilities. Right. So, in general, like, for example, this is the, convention that, how the antenna design evolution is happening. And then you can go to the Fractus antenna now become Igneon. Okay. So you can go there and find out. So how it is smartness, it is come, chip level. Now they are talking about chip level. And, any phased array, okay, if you implement the chain will be like this. You will have a baseband processing, then digital unlock, and you will have RF. In the transmitter chain, you will have these kind of arrays, and then you will steer the beams. You will, control the beams. The receiver side, you will have a RF, exactly opposite one. Yeah, digital to unlock, here unlock to digital. You will have a LNA over here. Here you will have power amplifier like this. Okay. Now comes massive MIMO. Okay. Maybe some of you might have waked up. Okay. So massive MIMO, it's, I see, here we have a single user, multi-user, multi-beam MIMO, many things are there. Here, what is the advantage we are getting is spatial diversity. Spatial diversity means, so spatial diversity and spatial multiplexing. So if you are having multiple antennas in the base station side as well as in the UE side, what you are receiving? You are receiving the same signal, or, multiple signal at a time through those antennas, right? Therefore, you are getting visual diversity and spatial multiplexing. So you see, instead of sending one data streams in one beam, one antenna, okay, one beam, what I'm sending through multiple beams, I may, so in single beam itself, I can send multiple data streams, and also I have multiple antennas to receive, right? In MIMO, with the help of MIMO concept. So what I'm getting, the same data, sometimes same data getting replicated in both antennas. You are receiving through both antennas, and then process it, so that, rake receiver concept and all that stuff, right? So you are, correctly decoding the signals. The second approach is spatial multiplexing, which means you are, the with the help of MIMO, what you're doing, you are receiving the two different data streams in two different beams, or two different through two different antennas, and beamforming in two-dimensional or three-dimensional fashion. Okay. So why we need beamforming here? That's why, this is related to phased array basically. That's why I'm covering here. So this is the, traditional antenna, 2G, 3G antennas will have this kind of pattern. I can tilt the beams electrically. That's all. So, but if I want to do vertical beamforming like this, I can use linear arrays. Okay. If I want to do two-dimensional beamforming like this, okay, horizontally as well as elevation wise, you need to obviously go for planar array. We'll have, the see, elevation, you are covering elevation as well as the horizontal. So then you need to have a go. It's called as three-dimensional, beamforming basically. Okay. Then this is how we used to cover this. Each user will be focused with the beam, so that, you'll have a better SNR, therefore the better throughput. And the advantages of MIMO is spectrum efficiency, superior data rates, whatever you can call, for example, higher SNR. Higher SNR means obviously indirectly what you are increasing. You are increasing the data rates and also spectral efficiency. Better energy efficiency, because you are unwantedly, you're not transmitting to any other direction. Signal quality at the edge, cell edges. So that is key part here. So when you are having, cell edges, right? So cell edges, this antenna will have a low gain. Therefore, the call drop will be more. Whereas here, the coverage vicinity is very high. Therefore, call drop is being limited over here. And then reject interference. Yeah, this is the example I wanted to show you. So here you can see, this is the broad beam I'm transmitting. I'm wasting energy, most of the energy, because my intended user is here. I'm wasting most of the energy, right? Whereas here, I'm just, pointing the beams, and then I'm saving the energy. That is one thing. And you can see here that, see this laptop you can see here is far away from the site, right? This particular technology, like broad beam, could not able to cater these users. Whereas here, with the help of beamforming, I can able to cater this user as well. Okay, that's why. And reject interference. See here, no, if any interference is coming from this mobile, I cannot avoid that, right? Whereas here, I can just send a null towards this particular mobile. Then I can control this. I can reject the reference. So these are all the typical use case you can see here that so many users are from, for example, it can be from buildings, multi-storage buildings, and also the bus, laptop users, mobile users, car user, everyone. So in order to cater that, we need to have this kind of scenario so that better throughput and better thing. So MIMO system perspective, this we have covered already. So I have 4 minutes to go. Just it's just a typical system perspective. Beamforming, processing, and all that stuff will happen over here in baseband. Then it will be given to RF lineup and amplifying it. This is how a typical system will look like. For example, you have a beamforming device, beamforming chips will be there. Then you will have a digital processing unit. Then ADC will be there. Sorry, unlock DAC will be there. Then your RF antenna, and it will be given to the antennas. Here, actually, basically the weights will be generated and then applied to these antenna elements, basically. Okay. Here, beamforming, processing, all that stuff, channel estimation. So that is a separate topic, basically. If I want to take, then I need 2 hours to cover that. Okay, so we'll just quickly go there. That these are all the some of the FPGA sites. So you just you will have a pre-coding baseband part. What is done? Pre-coding, calibration, and all that stuff. Okay, digital beamforming. Then you will have a FPGA to this do this lineup as well. So this is for the RF transceivers. So you will have a RF lineup elements in order to boost the signal. Whereas here the entire thing is basically digital baseband processing is done over here. Okay. Yeah, last slide. Okay, I hope I am on time. Okay, so last slide is like a simulation side. Okay, so if I want to design a phased array, I can use any tool. Like you can use MATLAB as well, but you will have somewhat ideal results. But if you want to analyze a 3D in a lighter fashion, then you can use ADS. And if you want to do further EM simulation, then you can go for CST or HFSS or anything. Okay. So in ADS, the advantage here is like either you can go for ADS come CST as well. Okay, ADS come CST. FICO you have, and also in Cadence also they have solutions, and many more companies they have solutions. See, they are going into system level simulation. System level simulation means you have seen, right, the RF front end and all that stuff. You can design an ADS over here, and then you are designing an array using 3D momentum layout, and then you can do whatever you want in the baseband and then send it to this RF lineup and then apply the excitation and then find out which direction my beam is. Okay, I can control the beam as well. The typical simulation will be like this. So here you can see I can I am just what input I am giving over here. It is given to this entire RF lineup and it is fed to these antennas, and then I'm controlling these beams. Okay, so here you can see that. Next, these are all the once you excite this, and then you can able to find out what are all the different parameters that I need. For example, input power, how much I have sent, and radiator power is what, directivity is what, gain is what, and radiation efficiency is what, then maximum density, effective angle, and so on. Okay. Then you can see that in this kind of a use case analysis you can do. For example, different beam directions, you can scan and watch it. Okay. So that's all. I hope I'm on time. Okay, 1 minute before I have completed. So thank you all for listening to me. If you have any questions, I will be more than happy to take up.
Yes, sir. One more question from Dr. S. Kannadasan, sir.
Yes, madam.
Any optimized technology to analyze the phased array? It is in chat box, sir.
Okay. Any optimized technology to analyze the phased array? Phased array. Okay. You mean algorithms or any other? I don't understand this question. Like basically, optimized technology means what? See, there are a number of algorithms are available. Okay, for example, Taylor series, T-Chebyshev. These are the traditional ones. Okay, there are a number of complex algorithms are available. And if you talk in terms of 5G, right, and massive MIMO, we have see how the beamforming will happen, right, in 5G. You will let me explain that. Maybe if that question, then I may answer that. See, you have a tower over here. Okay, you have 3 antennas. Let's say this is the maximum array. Okay, user. Okay, so now what happens is there will be a several transactions happen between the UE and ORU, radio unit basically, or a node B basically. What happens is, see, initially it will send the reference signal, and then SSB signals, DMRs like that will be there. Then it will measure the channel state. Channel state indicator will be there. CSA, RS based beamforming like that will be there. Okay, some of this channel state it will report. UE will report to the node B, and then it will identify, okay, where is my UE. Initially it will send the broadcast beam and identify where is the user. Any user am I getting any request from user. Then it will identify, okay, where is the user is. Then it will start project the beam towards that particular UE. Then we will have a, for example, beam refinement procedure is there, beam tracking procedure is there. When user is moving, beam tracking will happen, so that it is remain connected. So this beam forming, no, here the beam weights will be dynamically calculated and applied in the antenna elements basically. Okay, so these algorithms are running in the baseband chips, FPGAs. Okay, what will happen is, based on the measured results or feedback signals, it will calculate the weights, apply to the antennas, and then steer the beam accordingly, and whichever direction I want. So that way, but optimized technology, I don't know what is this expectation. Yeah. Any other questions?
Participants, if you're having any questions, kindly ask through chat box or unmute your.
I hope it is very clear, or neither clear, not not clear. I don't know. I hope everybody's.
Yes.
Thank you.
Okay, sir. Thank you very much, sir.
Yeah, thank you, madam.
And thank you all the participants for attending peacefully.
Thank you, sir.
Thank you so much, madam. So thank you so much for for the opportunity, and thank you all those who have listened to me. And afternoon time, it is highly tough time to listen such a lecture. So, but it's okay. Thank you so much for all listening to me. Thank you.
So, thank you, sir.